Our next speaker is going to be Alexei Vazquez, who is an assistant professor in the Cancer Institute of New Jersey, and the title of his talk is up on the board.
Thank you, Arnie. In the last 30 years, cancer survival has actually increased quite a lot, by 10%. So in the early 70s, it was around 70%, and today it's reaching 80%. And hopefully, with the continuing of cancer research, we can keep pushing up this survival rate. Now, part of this success has been thanks to the development of new chemotherapeutic agents like cisplatin, Taxol, and more recently, some target therapies that are actually provide us with an arsenal of compounds that we can use to treat cancer. However, these numbers also tell us that there is a fraction of the cancer population of individuals that are diagnosed with cancer that do not respond well to current chemotherapeutic treatments. And the question is how we can try to go and identify some new compounds, new treatments that can be used for treating those patients. And one of the possibilities to do that, and it's also something that becomes feasible today, is to use the knowledge, the aggregate data that have been accumulating all these years or following all this intense research in cancer. And this data is now sit there in the public domain, and maybe by looking these aggregate data sets in a careful way, we can try to infer or trying to find out new treatments that can improve the survival rates by just looking at the aggregate data, which is something that probably was not possible before because of the focus on individual research topics. So to be more specific, I'm going to talk about how we can try to identify novel cancer treatments by first stepping a bit out of the problem and try first to understand what is the general trends, the general patterns or responses of tumor cell lines or normal cell lines to treatment with small molecules that could have potential for chemotherapy. So our initial focus will be on understanding those patterns. And then after hours, once we understand what is the general trend, what is the null reference model of responses of cell lines to small molecules, then how we can use that information to try to infer new compounds that could then potentially be used for therapy of cancer. So for that, I'm going to use, as I said before, data sets that have been accumulated in time. These are data sets that sit in the public domain, so in principle, anybody can take a look at them, or you just have to be careful how you look at them. In particular, I'm going to analyze two data sets. The first one is a compilation of reports of responses of tumor and normal cell lines to different chemotherapeutic agents. This is an aggregate of about 100 compounds and have been obtained from reports of different labs, and also using different protocols, which is an additional caveat of this dataset. However, it has the advantage that we can take a look at what are the main differences, statistically speaking, between the responses of normal and tumor cell lines to chemotherapeutic agents. The second dataset has the caveat that is only for tumor-derived cell lines. So this is the anti-cancer screening developed by the NCI and NIH. So they have tested like 50,000 compounds against those 60 cell lines, and as a consequence, and using the same protocol, which is quite important, which makes this data of more quality for making predictions. And so using these two data sets, we're first going to try to understand what are the typical patterns or responses of cell lines to small molecules. So the typical measurement that will be reported in this experiment will be a growth inhibition assay, as shown in this figure for the MSF7 breast cancer cell line and upon the action of doxorubicin. And typically this curve, as you increase the drug concentration, you will see a reduction of the survival of the cell lines, and so as a consequence, you will see a decrease in the growth, an increase in inhibition, and therefore reduction of the size of the population. And a typical magnitude that is usually reported, extracted from this curve, is the IC50, which is the drug concentration that is needed to inhibit the growth of the treated cells, 50% relative to the control untreated cells. And this is the typical measure that is reported, and is the measure that we are going to use from now on to try to characterize the responses of cell lines. Whenever the IC50 is small, it means that the cell lines are more sensitive to that compound. Whenever it's high, that they are less sensitive and potentially resistant. Now, since we are going to deal with several compounds, we need to be careful about normalization of this data, so how we can compare different compounds. So these plots here are showing what is the distribution of the IC50 for 2 compounds across the 60 sample of the NCICT screen for doxorubicin and Taxol. So each symbol there corresponds to a cell line, and in the x-axis you have the IC50 in a logarithmic scale. The first thing to notice is that the wide spread of the IC50s. So you can go for something. You can go for something like those, like 10 to the minus 8 molar, so like which is 100 of a micromolar, and you can go also to much higher values of 100 micromolars. So it's really there is a wide variability of the IC50, and that's why also it's convenient to work in a logarithmic scale. And second, notice that different compounds might work at different range of concentrations. So in this case, we see that Taxol the activity of Taxol kicks in at lower concentrations. So if we want to compare these compounds, it is fair to displace their IC50 relative to their means. So you can shift the compounds relative to the mean, and you can focus, instead of focusing on the absolute IC50, you can focus on the relative variation of the IC50 across the population of cell lines. But to do that, you just can subtract the mean and focus on the variability around the mean. So if you put these considerations together, you can get a normalized magnitude that is essentially like a log ratio between the IC50 and the mean IC50 across cell lines. And this is the magnitude we are going to focus on from now on. So I would call it the IR50, and it's essentially a relative IC50 in a logarithmic scale. So after this normalization, now we are in a position to ask the question, what is the distribution of this magnitude across all cell lines and compounds? So essentially, for each compound and cell line, you get a measurement of this IR50, and then you can say, what is the histogram of that measurement? And this can be informative of what is the general pattern of responses of cell lines. And this is what is shown in this figure. So in the y-axis, we have these relative IC50s divided by the standard deviation, just for the purpose of normalization. So around 0 here means that the values are at the mean. And when you move to the left, to negative values for the IR50, you move to low IC50, and when you move to the right, you move to high IC50. And here in the y-axis, you have the frequency of number of measurements that have been observed in a given range. And as you can see, that this distribution have 2 distinctive features. One is that it have a peak around 0, which essentially means that most responses are concentrated around the mean. So it's not bimodal, it's unimodal. And second, that there are 2 tails to the left and the right. That on the left, you have the good responders, and on the right, you have the bad responder, or less sensitive or potentially resistant cell lines. The first question you will then ask is, so where are located the normal cell lines and where are located the tumor cell lines? You would expect that probably, likely, if all what we know is true, that most of the normal cell lines should be in this area, while most of the cancer cell lines should be in the low IC50 area, because of the expectation that most chemotherapeutic agents target preferentially tumor cells. So this is what is shown in the next slide. So it's the same histogram for the relative IC50, but now splitting, pulling apart the normal and cancer cell line. And as you can see, yes, in average, you can see that more or less the distribution for cancer cell lines in red is shifted to the left, to the low IC50 region, while that for normal cell lines is in blue is shifted to the right. However, I mean, these distributions have a significant overlap among them. So what this means that in average, yes, I mean, cancer cell lines respond better to chemotherapeutic agents, and this is in average by a 2-fold reduction. But still, there is a lot of overlap. So, and this is put a challenge to therapy with chemotherapy, because it's hard to set the concentration range where you will try to kill the cancer cells, but not lead to toxicity of the normal cell lines. You can actually do the same analysis, but now focusing on a specific compound. So the one I showed you before was a compilation for all compounds, but you can try to look at a specific compounds and see if this holds. And this is what is showing this slide from methotrexate, which is an antimetabolite and an antifolate. And as you can see, the pattern is similar, although methotrexate, you see a more split between the populations of normal and cancer cell lines. Still, you also observe, again, a significant overlap in the middle. And you can see that here there are several, a high fraction of tumor cell lines that are less sensitive to methotrexate, and so that can cause a problem. So since these cell lines respond more or less the same as the normal cell lines, and potentially those are cell lines that are resistant to treatment. So the question is what we are going to do, how we can tackle this problem. So for doing that, I'm going to try first to jump to the other dataset of higher quality, the NCI60 dataset. That is a dataset for tumor cell lines only, but contain more compounds. And the first thing one can do is try to see whether the observation, the histogram that we saw before for the literature dataset holds for the case of the NCI60 dataset. And this is what is shown in this slide, and the histograms are quite similar. Probably the main difference is that in the NCI60 data, you have more compounds around the mean. And this is probably because this data here from the literature is enriched on compounds that actually have an anti-cancer activity, that have been shown to have anti-proliferation activity, while these ones contain a lot of compounds that were experimental, that do not have actually a good inhibitory activity. So what this says is that more or less the observations remain, so that we can be confident that this histogram that we observe is not a caveat of the literature dataset, so it's more or less the general trend of the responses of cell lines to small molecules. And now we can now say with this confidence at hand that we can try to say, well, what we can do to tackle this problem of the fact that the distributions between the cancer and normal cell lines are quite entangled, quite mixed. How we can go around and design cancer treatment. So one of the obvious things to do would be to use a high dose treatment, where you can put the bar here, where you can set your concentration around here, and by doing that, you take care that you are inhibiting the growth of most of the population of cancer cells. However, you are also inhibiting the growth of normal cells, and therefore this is potentially toxic for all the population cell in the body that is growing, meaning stem cells, immune system, and response to injury. So therefore, although this potentially can target all cancer lines, is probably quite toxic, as you probably know, are aware from the clinical studies. The second approach, which is the one that we are going to be more push more, is the one using low concentrations. So we're going to set a dose that is low enough that you can avoid the issue of toxicity, so you will not be hitting most of the normal population, the normal cell population, and you will be mainly hitting this small fraction of cancer line here. So this have the side effect that you still will have a lot of resistance. And therefore, you need to now to design strategies of how we are going to deal with the issue of resistance. So the next slide is going to be about two different ways to tackle this issue. How to, using a low dose therapy, how you can try to avoid this issue. And as you expected, these two types of approaches have been actually used in the past. We are just trying to make use of them again, but now we're going to use new data to try to infer new compounds and new treatments. So as I said, we're going to push forward this approach of using a low dose treatment. So if we set the bar here, therefore we're going to say that the cell lines that respond well to treatment are those measurements that are concentrated here on the left tail. So we're going to, for now, we're going to define that a cell line responds well to a compound if their IC50 is in this region here. So, and it's a region where we can say with high confidence that the IC50s are low. So essentially, for now, good response would be equivalent to say that with about 95% confidence, the IC50 is low relative to both the mean for the population of normal and cancer cells. So after doing all this normalization, after all this analysis, when you end up with a high-quality dataset, which is a summary of the original response matrix that we use as input. So we transform the response matrix of all cell lines against all compounds in the dataset and the NCI60 dataset into this graph here, where on the left you have the cell lines, on the right you have the compounds, and you connect a cell line to a compound whenever the cell line responds well to that compound. And as I said, respond well means in the sense that I said before, that with high confidence the IC50 is low. So this is higher quality data that now we can use to try to infer new treatments. And part of the success of the prediction that we're going to come after are due to the fact that we boil down all the data set into this more high-quality data set. So that's why it's important to first focus on the general patterns of the responses, define a null model, which is the histogram I showed you before, and then from that null model, identify who are the outliers that are responding much better than the rest of the population. And thanks to that, you get with a high-quality data set that then you can now use with more confidence to try to infer new treatments. So the main features of this graph is that first, there's no drug that targets all cell lines. That's probably you will expect it. And then the second is that at least one compound, for each cell line, you can at least find one compound that targets that cell line, which is a good news because it means that in principle, we should be able to identify compounds to treat all the tumors that are represented within the NCI-60 dataset. So the question is now how we're going to go identify them and how we're going to design strategies to treat those tumors. So one approach is the combination therapy. This is one that is actually used, but let's see how we can implement, how we can infer good combinations using this data set that I just described. So combination therapy can be looked at in different ways. The particular way, specific way I'm going to look at it is in the sense of coverage. So let's try to look for a combination of two drugs or more drugs that together they will target most of the population of cancer cells. As I said before, no drug, here, drug one, no drug target all cell lines. So you can try to bring along a second drug that will take care of those cell lines that are resistant to this drug and vice versa. So such that together they cover most of the cells. Of course, you would like to look for those combinations that cover the most of the cell lines because of the issues of economical reasons and potential toxicity. So the question is, can we find drug combinations that have maximal coverage, and what are those combinations? So you can go ahead and go at that graph that I showed you before and trying to identify those combinations that have the maximum coverage, and this is what you obtain. So actually, the best combination among FDA-approved drugs that were tested within the NCI-60 screen is a combination of an antifolate and an mTOR inhibitor. See, methotrexate and everolimus. So here, approximately, using these two drugs, you reach almost like 80% coverage. So you can be kind of assured that 80% of the cell lines in this data set have low IC50 for either methotrexate or everolimus. So this is the plain prediction that you will obtain doing this kind of analysis. You can actually improve this number if you extend the search to compounds that are not FDA approved, but were tested within the screen. And actually, you can find that the best combination among all possible combinations of two drugs in this dataset is again a combination of a methotrexate derivative in this case and everolimus. And this is very reassuring because the fact that we recapitulate the same observation when you extend to all compounds. And so potentially the prediction here is that yes, probably with combination of two drugs or potentially three drugs if you extend the search to a larger collection of tumor samples, with 2 or 3 drugs, we should be able to treat all tumors. And more important, using this approach, you can identify which are those combinations. And this certainly is the one that scores more. Now, there is the question whether this holds. I mean, how to validate this in other scenarios. And certainly, if you are interested in something about methotrexate and you work in CINJ, you're extremely lucky because you can just knock the door of Dr. Bertino's office and ask about it. And as a matter of fact, happens to be that Bertino and Avali and their colleagues at CINJ, they were actually already investigating this combination in lymphoblastic cell lines. And what they observed is that actually the addition of an mTOR inhibitor to the treatment of methotrexate increased the sensitivity quite a lot, by 100-fold, according to their report. So what can be taken as a validation for the approach that we were taking about identifying drug combinations, so that those combinations that we found actually can be shown to be, in this case, in particular case, is actually good combination, is synergistic. Although I have to say that in our approach, we were not looking for synergy, we were looking for coverage, but actually, in addition to that, happens that it's also synergistic. So this is definitely a very promising combination, and it will be worth testing whether it's actually can improve treatment in the clinic. So in the last part of the talk, I'm going to switch to another strategy that will be more in the direction of personalized medicine. So the strategy before was kind of agnostic regarding what are the specific transformations that the tumor had. So we were just looking for combinations that will target all tumors. Here, we are going to use the information we know about tumors. For example, we can have a specific tumor cell type, and we would like to see which is the best compound in our library that can target that specific tumor. So it's a more personalized approach. And this is work that I'm carrying on in collaboration with Darren Carpizo, Xin Yu, and Arnold Levine at the Cancer Institute of New Jersey. So And as an example of this, we're going to use tumor with a mutation in PP3 to show how the approach goes. And why we started with PP3? Well, because PP3 is probably the most prevalent alteration you can see in tumors. In spite of that, it is known that most of the chemotherapeutic agents that are in use do not target well tumors with a mutation PP3. For example, within the NCICT dataset, you can go and look at a collection of about 132 standard chemotherapeutic agents, and you can check whether these agents target better the cells with wild-type PP3 or those with mutant PP3. And what you find is the vast majority, here highlighted in red, are more effective when they encounter cell lines with a wild-type PP3, and cell lines with a mutant PP3 are quite resistant or much less sensitive. There is only one exception, and there are the antimitotic agents like Taxol. In this case, they don't see difference. According to this dataset, Taxol don't see a difference within the cell lines with wild type and a mutant PP3, which just indicates that the mechanism of inhibition, growth inhibition by Taxol is not through the PP3 pathway. But still, it is not specific for the mutant cell lines. So the bottom line is that among the chemotherapeutic drugs that are in use in the practice, there are no agents that target specifically cell lines or tumors with a mutation PP3. And so that's what makes it quite important to identify those kind of compounds that could potentially target tumors with PP3 mutations. And as a matter of fact, those two evidences put together, the bad response of cell lines with mutant PP3 to the chemotherapeutic agents that are in use, you could expect that what is shown in this slide, that the survival of patients with a mutation in PP3 is poor compared to those that have a wild-type PP3. And as you can see, those patients with mutation PP3 have a more do not survive well to treatment, and so they die earlier. And this can be shown from here for two different tumor types, B-cell lymphomas and breast cancers. Although here you have another variable that can be influenced, you can see still that those with the mutant PP3 are the ones with the worst prognosis and survival. So, since we are going to now try to identify compounds that are specific for that target preferentially cell lines with mutation PP3, we have to be very careful with which kind of PP3 mutations. Because it is known that the prevalence of PP3 mutations depends on the location. And this is what is shown in this slide. So most of the mutations lie on the DNA binding domain of the PP3 protein. There are a few hotspots, specifically position 248, amino acid 248 and 273, that are located at the region where the PP3 protein binds to DNA. And there is also a hotspot in 175 that is essentially at the zinc pocket. And also this mutation is in high prevalence. So when looking at PP3 mutations, we're going to be specific, and we're going to focus mainly on these mutations rather than the entire population of mutations of PP3. So, and how we can try to identify compounds that will be specific for targeted specifically cell lines with mutation PP3, well, this is the kind of approach we designed. So we will use a typical case control study. So we are going to use as control cell lines with wild-type PP3, and in the NCI you have about 19 cell lines that have a wild-type PP3. And then as cases, the tumors, the cell lines that we would like to target, we usually use 9 cell lines that have mutation at position 248 and 273. So specifically, we're going to search for compounds that will target more these cell lines than those with the wild-type PP3. And to do that, to do in a quantitative way, we define this score function here, which essentially is the fraction of good responders among the cells with a mutant PP3 times the fraction of bad responders among the cells with a wild-type PP3. So this score essentially tries to maximize good response in the population of cells with mutant PP3 relative to those with a wild-type PP3. If you apply this score to the NCIC, to the 50,000 compound in the NCIC dataset, you can rank them according to this specific activity towards cells with a mutation in PP3, and this is what you obtain. As you can see, most of the compounds are not specific towards PP3, as you would expect. The majority of them are not. There is a few compounds in this region there that do not care about the PP3 status. If you check at them, there is no significant difference in their action with respect to mutant or wild-type cell lines. And there you have Taxol, the compound I just mentioned before, that have a score around 0.1. But still, the good news is that we can find a few compounds, there are a few, but they are there, that have high specificity towards cell lines with a mutation in PP3. And the question is, so the plain prediction here is that these compounds are potential are candidates for treatment of tumors with mutation p53. And the rest of the slides are going to be just to show you the initial steps that we are following in trying to validate that these compounds are actually act towards cells with a mutation p53 and what is the mechanism of action. So we did some validation in some mouse cell lines that actually was developed by Dimmer and collaborators in the Arnold Levine lab in the early 90s. This cell line is a p53 new cell line that and then has been transfected with different p53 mutants, including the 175, 248, and 273. They are the ones that we are focusing on. And what we're going to see is whether our observations in the NCICT dataset holds in these cell lines. That in this case, in particular for these 3 mutants, the cell line is isogenic except for that specific mutation. And as a control of a cell line with a wild type p53, we're going to use the 3T3 mouse fibroblast cell line. So this, so what we did, we took the first compounds and tested them, and this actually was the one that showed better signature of specificity to cell with mutant p53. As this is just a growth inhibition curve as the one that I showed you before. So here on the y-axis you have survival % of the treated cells relative to untreated cells, and here on the x-axis you have the drug concentration. So this compound actually, as you can see, the cells with wild type p53 are quite insensitive to the compound, as predicted by the analysis of the NCICT data. However, the cells with a mutation p53 or p53 null in blue are quite sensitive to the compound. So they actually are micromolar concentration there, or below micromolar concentration, they are already showing manifesting growth inhibition. It was interesting that the 175, that was actually not including our initial screen, actually is even more sensitive than the other mutations. So it looks that there are some allele-specific effects here that deserve further investigation to find out why, what is the mechanism of action. It's also interesting to know that there is another compound with similar chemical structure that shows a similar behavior, although less extreme. Again, here you can see for this second compound that the cell lines with wild type p53 are less sensitive to the drug compared to those with mutant p53 or p53 null in blue. And again, you can see that also in this case, the 175 is the most sensitive. It's relatively more sensitive than the other mutants. So these 2 compounds have similar chemical structure, and the one that we are focusing more on our analysis. Regarding their structure, they are iron chelators, so this structure here, chelate for iron. And we are trying to see how they act, so how they, what is the mechanism by which they act towards cells with mutant p53. So the first hypothesis, of course, was to check whether with treatment of the drug you get induction of the p53 targets, maybe because it restores the conformation of the p53 protein, and it doesn't. The second thing that we look at is where this drug-induced interaction with p73. And why we end into that is because there are reports in the literature that some p53 mutants actually interact with p73, and by doing that, they modify the response of cell lines through the p73 pathway. So this is the second avenue we look at. And the way we look at it is we did some immunoprecipitation assay with an antibody for p73. And the hypothesis was that if the mutant p53 interacts with p73 in the presence of the drug, then if you do a pull-down assay, you will find both the p73 protein and the p53 protein. However, if you have a wild type p53 or no p53 at all, you will not get p53 in the pull-down experiment. And if you have the mutant p53 but not the drug, you will not see p53 neither. So this would be the prediction of if there is actually an induction of this interaction here. And this is actually what we observed. So these are the Western blots from that experiments. In this case, this is for the mouse cell line that was using the growth inhibition assay. So here on the bottom, you have what is the status of p53. The null is here. The wild type is here, emphasizing in blue. And the 3 mutants are emphasizing in red. As you can see, if you have a no p53 or a wild type p53, you don't see p53 in the pull-down assay. It doesn't matter where you have the drug or not. So this corroborates what we were saying before, that this is specific for the mutants. And when you look at the mutants, you can see that in the 3 cases, if you have the drug, you also pull down p73. So it means that this is inducing interaction. In the case of the 273, it looks that there is an interaction previous to the induction by the drug, but it's actually enhanced by the action of the drug. So it looks like it's really the mechanism of action is through induction of this interaction. And we actually corroborated this observation in a second cell line, in a human cell line, that is p53 null, that has also been transfected with a p53 that is inducible by doxycycline. So whenever you add the drug, you remove the expression of p53, and whenever you don't have the drug, you have expression of p53. So here on the left, you have the data, the results obtained without the drug, and as you can see, in no case there was a pull down of p53, as we were expecting. When you add the drug, if you have a cell line with no p53 or with a wild-type p53, you don't get p53 neither. However, if you have either of these mutants and the drug, you pull down p53. So this again corroborates that the potential mechanism of actions of these compounds is through induction of an interaction between mutant p53 and p73. And we are further investigating how this happens. I mean, whether this is due to the conformational change or what is the mechanism behind it. But certainly it's giving us a good lead that this is actually a real effect, not only an association with response, it's also there is a mechanistic potential mechanism behind it. And so we're kind of confident that this compound can have potential for the treatment of tumor with mutant p53. Maybe the compound itself don't make it through, but an equivalent or the concept itself can go through of how to treat tumors with a mutation in p53. So I want to conclude saying that this kind of work can be extended to other mutations. And we are only limited by what are the mutations that are present in the NCICT cell lines. But as you expect, they will be enriched for those mutations that are more prevalent in the tumor population. In particular, you can look at the one of p53 that I just mentioned. But you can also look at p10 mutations, cell life compounds that will target specific cell life mutation in p10. We are in progress work on that. You can look also at those with mutation in KRAS. And it's interesting that the first compound that came out here is gemcitabine. That is actually one of the frontline treatments for tumors with pancreatic tumors, where it's known that there is an enrichment for KRAS mutations. Also, when we went to BRAF, we looked for compounds that will target specifically a cell line with a BRAF mutation at the amino acid 600. And the compound we found actually is in clinical trials, phase 2 clinical trials for treatment of tumors with BRAF mutations. So this, again, is just evidence that is corroborating that this analysis is working and gives us confidence that the predictions that we are obtaining are of high quality. Furthermore, that we also have novel compounds that can be tested or can be further validated for their action in tumors carrying these specific mutations. And furthermore, we're also working on other type of alterations. In principle, you can look for compounds that target tumors with some specific alteration. It doesn't need to be a mutation. All the limitations is rooted in the fact that what you can find, if you can find enough cell lines with the alteration and enough cell lines that do not carry alteration. This is actually a major problem analyzing this data set because it's very heterogeneous, so you have to be very careful choosing your cases and controls. And I want to conclude saying that this work would not be possible if it wasn't for the collaboration with Carpizo, you and Levine. So essentially, Carpizo and you are the ones that have been leading the experimental side, trying to find the mechanism of action, and also thanks to a lot of insightful suggestions from Levine. And with that, I conclude, and thank you for your attention.
So I was curious that the combination of everolimus and methotrexate was so effective. Since the mTOR inhibitor is obviously inhibiting the major nutrient-sensing pathway, and methotrexate is an anti-metabolite, have you explored the possible mechanism behind that synergy?
Bertino and Avali and their colleagues are actually on top of that. So they themselves have been working quite a lot on that, and they have more or less figured out how it works.
And?
So I don't recall now exactly how.
All right, and the other question is that the major problem with getting tumor cells to respond to chemotherapy is that we just don't kill them all. Yep. And part of that problem may be due to a number of different reasons, including genetic heterogeneity within the tumor, or tumor cells that are residing in a niche in vivo that alters their cellular response to chemotherapy. Have you looked to see if your model is the same or different in an in vivo setting where you can recapitulate the, tumor dormancy in effect?
So we haven't looked on that yet. So but definitely something that we have to look at that, because exactly what you said, that this, and also one have to be careful where the growth inhibition is by cell cycle arrest or by apoptosis. The compound that I was showing them, the main one, is actually through apoptosis, but the other one, no, is just through cell cycle arrest, so that's one. So, but we haven't looked into that yet.
Right, and cell cycle arrest might be undesirable because that's theoretically a reversible.
Yeah. It's quite interesting. They have very similar chemical structure, but one does inhibit growth through apoptosis and the other one don't.
So you're going to get the answer to your first question by the next questionnaire.
Just to follow up on the methotrexate rapamycin combination, what's interesting about rapamycin, it actually downregulates dihydrofolate reductase, so that even potentiates the combination even more. There is a clinical trial now. We were preparing a clinical trial, but the University of Pennsylvania Children's Hospital beat us to it, and they're getting some pretty dramatic responses in kids with resistant childhood leukemia.
Great.
Great job, as always, Alexei. Just a question, could you apply potentially the same mathematical methodology to the clinical trials data? Meaning there are plenty of phase 2 trials showing single agents, showing combinations across many, many different tumor types in the literature. Any thoughts on those databases?
So I was exploring that possibility, and I think in principle it's possible. One have just to shift, we have to focus on tumor types rather than in patients. So because you cannot treat a patient with a library of compounds, of course, it's not feasible. But you can have, if you subdivide the population by tumor types and you collect the survival data from treatment with different compounds, you can try to analyze that data and infer something from there. It will be a bit limited on the compound side because the libraries of compounds that are actually used in practice are small, and from there it's hard to infer novel compounds but you can infer definitely combinations that could work better from that clinical data, and something that I've been thinking about how to do it.
Early on in your presentation, you had something that showed like a bimodal response for, I don't know if you can find that slide. Yeah, that one right there. That suggests in personalized drug treatment, I think you want to sort of isolate the responders from the non-responders. So that would be, you kind of see that there in the red, you have responders on the left and the non-responders on the right. But when I saw this, I thought that this might also give a possibility of toxicity stratification, where it looks like there's a difference in toxicity between the blue ones. Right?
Yeah.
And so if you could stratify patients not only by response, but also maybe by toxicity, changing the doses, which I think is not done right now. Is that right?
Yeah, this is a very good idea, as a matter of fact, and yes, in principle, it should be possible to do. So there are other things that one can look at. One is the one you're saying, why these cell lines are more toxic than this one, definitely. Another thing you can look at is why it's giving resistance to these cell lines. So, but definitely, yes, it's possible, provided one will have a data set where there will be also molecular information about these cell lines. It should be possible to do.
Okay, we have a break now.